Now what I want to talk about is the distance or the distance traveled and versus the displacement, or sometimes they'll be more explicit and say it's the displacement vector. Okay, so either way. And so then what we get is that the distance traveled is again a scalar quantity. So either the distance or the distance traveled. It's a scalar quantity. Which gives the length of the path motion followed by our object of interest. So again, what we have is this is again another scalar quantity, and it just basically tells us, the length of the path of motion type of idea. Okay. Now, when we get into talking about the symbols that we're going to use to indicate the distance, then this is where we're going to see that there's somewhat of an issue because in general, there is not a symbol. And that's pretty telling because what that means is that means we're not really going to use this concept a lot, because if we used it all the time, there would be a symbol for it. So lack of a symbol means that this is probably not going to be, highly used kind of things. So they actually might write out distance or something like that. Or sometimes they'll use a D, but not always. Okay. And if we come in and we take a look at our SI units, then again, it's another length. So therefore, it's going to be in meters, like so. And one thing that I want to point out is that, in general, there's not really a formula to give us the distance of some sort of path, especially if that path is some sort of arbitrarily curved path. Okay. Now, in one dimensions, we just travel along straight lines, and there's a distance formula between 2 points on a number line, and we can just use it. But other than that, in 2 dimensions, if you do some sort of serpentine path from point A to B, then there's not necessarily a formula to tell me how long that path is. Now, if you travel in straight line segments or portions of circles, then we can do things. But if it's just some arbitrary curved path, there isn't necessarily a formula. So note, in general, there is not okay. There just isn't a general formula. Okay, so that's worth noting. And now we can go and we talk about our displacement or the displacement vector. I mean, if they use the term displacement, it is indeed a vector quantity. But again, they might say vector so it is a vector quantity. And it's going to be the shortest directed distance from where the object started to where the object ended. And the important piece is that we're going to go from where we start to where we end, and I don't care how you actually move. Okay. So let's do like a little. We're going to start here. The motion's going to end here. So that's our path of motion. Okay. And like I mentioned, there's not really a formula to tell me how long that path is. Not a general one. But since the object started here and ended there, you can go, oh, it went this way. And this will be the displacement. Okay. And so then what we'll find is that how we will denote this displacement is we're going to use a little symbol that is the Greek letter delta. And how do we interpret delta? I mean, I know you know what it means mathematically. You know, graduates.
Change.
Yeah, what was that?
Change.
Yeah, it's the change in. That's exactly right. So it talks about the change in whatever we're deltaing. And what we're going to delta to get the displacement is the position vector. So in this two-dimensional example, this would be delta vector r. So the change in the position vector will give us the displacement vector. Okay. And so then that's kind of, like I said, an interesting thing to take a look at, because if we're back here, then we would go from where the person initially started to where they ended. And we could go ahead and calculate that displacement vector. Okay. And so if we wanted to look, we could calculate this. So the displacement vector is the change in the position vector. And in physics, this is always going to be interpreted as being the final minus the initial. And there's really no exceptions to that. So we'll do the final position vector minus the initial position vector, like so. And since these are coded into the coordinate system, we can take that this is going to be our -5 meters minus our positive 10 meters. And we get -5 minus positive 10 is -15 meters. And so then what we'll see is that that's the magnitude here. This is 5 plus 10. This is indeed 15 meters long, and it points left. Left is negative. And so in our coordinate system, this would tell us that this is, west. Okay, so 15 meters west is the displacement vector. Okay, and automatically comes out like that. So when we calculate change in anything, it's always going to be that final minus the initial type of quantity. And there we go. Now, notice that, this may not actually be related to the distance that the person traveled, right? Because our person could have started here at this initial point, headed this way, and then flipped around and then headed back, or even headed further back and then flipped around again. I mean, so that could be the actual path of motion, in which case the distance traveled is much, much longer than the 15 meters for the magnitude of the displacement. And so in order to calculate the distance, we would probably need to know what this coordinate was, and we calculate that distance. And then from here to this coordinate, we calculate that distance. And then from here to that final position, we calculate that distance, and then add all three of them up, and we could get how long the path was. But again, there's not really a simple formula per se that will give you the distance traveled. Okay.